Imagine holding a spoon. Now imagine that spoon is filled with a piece of a star, no larger than a sugar cube, but weighing more than Mount Everest. This isn't science fiction. This is a neutron star, one of the most extreme and bizarre objects in the known universe. Neutron stars are born in death, the death of massive stars, to be precise. When a massive star, usually more than 8 times the mass of our sun, exhausts its nuclear fuel, it can no longer hold up against gravity. The outer layers explode in a spectacular supernova, but the core collapses inward under its own immense weight. What remains is either a black hole or a neutron star. In this violent collapse, something remarkable happens. The atoms in the star are crushed. Electrons and protons are forced together, creating neutrons. What's left is a sphere about 10 to 20 kilometers wide, roughly the size of a city, but with more mass than the sun. It's like cramming an aircraft carrier into a grain of rice. The result is an object so dense, so compact, that a single teaspoon of its material would weigh several billion tons. That's 1 trillion kilograms in a spoon. So here's the big question. If neutron stars are this dense, why don't they just keep collapsing and become black holes? The answer lies in a delicate balance between gravity and quantum mechanics. Once a star's core collapses into a sea of neutrons, it reaches a point where gravity is almost strong enough to overcome everything, but not quite. The neutrons, although neutral in charge, still obey the rules of quantum physics. Specifically, they resist being squeezed into the same place at the same time, a principle known as neutron degeneracy pressure. This quantum force, strange as it sounds, provides enough pressure to counteract gravity. It halts the collapse, but this balance is fragile. If the mass of the collapsed core is too great, typically around 2.2 to 2.3 solar masses, even neutron degeneracy pressure fails. Gravity wins, and the star continues collapsing until it becomes a black hole. This threshold is called the Tolman Oppenheimer Volkoff limit. Think of it as nature's tipping point. Stay under it, and you get a neutron star. Go above it, and you disappear behind the event horizon of a black hole. Neutron stars, then, are survivors, stellar corpses, teetering on the edge of oblivion. They didn't become black holes because their final mass, after the supernova, wasn't quite heavy enough. They are, in essence, the densest objects in the universe that aren't black holes. And that's what makes them so fascinating. What's inside a neutron star? The truth is we don't fully know. The outer layers likely form a solid crust, made of tightly packed nuclei, but deeper in, the pressure and density become so immense that atomic structure breaks down. The core may be filled with superfluid neutrons, or perhaps even more exotic matter, like hyperons, or a soup of free quarks. These are conditions we can't replicate on Earth. So neutron stars serve as natural laboratories for extreme physics. The gravity at the surface of a neutron star is mind-boggling. If you could stand on it, which you absolutely couldn't, you'd weigh billions of times more than on Earth. Even light struggles to escape its pull. And yet, they're not black holes. Light can still get away, though it is heavily redshifted. You can still see them, or at least detect their radiation. In fact, if a neutron star were to gain more mass, say by absorbing matter from a companion star, it could eventually tip over that mass limit and collapse into a black hole. Some binary systems in space are thought to be doing exactly that, slowly feeding one star until it can no longer resist gravity's grasp. At that point, the neutron star would vanish, leaving behind only a black hole and a gravitational echo of what it once was. So to sum up, neutron stars exist in a narrow window between stability and collapse. They are born from destruction, yet resist becoming nothingness. Their mere existence is a cosmic balancing act, one governed not only by gravity, but by the strange and beautiful laws of quantum physics. They remind us that the universe is not only vast, but filled with delicate thresholds, where extremes collide and something entirely new is born. They are not just dead stars. They are monuments to the limits of physics, dense, dark, and endlessly mysterious. Thanks for watching. If you enjoyed this deep dive into the weirdest stars in the universe, Don't forget to like the video, subscribe to the channel, and let us know your thoughts in the comments. Until next time, stay curious